Hello mathematicians, today we're going to learn about writing differential equations by identifying proportional relationships. So if we have a differential equation that we know is proportional, it would be of the form dy dx equals some constant k times y. This is some constant. If we have a relationship that's inversely proportional, it would be written dy dx equals some constant divided by y. So let's do an example. The rate of change of A with respect to B is inversely proportional to the cosine of B. Which expression could be a differential equation that models this situation? It says rate of change of A with respect to B. That means dA dB. And here we have cosine of B. And it is inversely proportional. So if we know it's inversely proportional, that means we have to have a fraction with cosine of B on the bottom. So we'll have dA dB equals some constant divided by cosine of B. So let's look at our options. Well, option A and B have directly proportional relationships. We don't have a fraction, so it can't be those. What's the difference between C and D? It's in the initial differential expression. So here we have rate of change of A with respect to B, so A must go on top, so it must be C. Notice we have this 5 here. They can put any number they want because k is just some constant. Let's do another example. Let P of t represent the population of people on an island with the coronavirus. The population grows at a rate directly proportional to the population size. Write a differential equation to model this situation. So we have directly proportional here. So we're going to be using our first case. The population is growing at a rate. So if we have a rate of the population, that would be p prime of t, or dp dt. These are the same thing. And if it's directly proportional, we're going to have k p to the population size, which is p. Usually, the variable that's on top is also the variable on the right-hand side. That wasn't the case in the first example, but it is more often the case. But make sure you read the question. So it's proportional to the population size, so we have Kp. Now, it asks us to write a differential equation to model this situation. Then solve it through separation of variables. So we've written our differential equation. Now we need to solve it. In order to solve it, what's our first step? We need to separate our variables. So we're going to multiply by dt on both sides to get dp equals kp dt. Now what do we need to do? Well, we need this p to go to the other side. So I'm going to divide p on both sides. So I get 1 over p dp equals k, these cancel, dt. Well, if I want to solve it now, what do I need to do? Integrate both sides. If I integrate 1 over p, that is ln of p. If I integrate k with respect to t, well, that will be k times t plus c. Now what do we need to do? Solve for p. Well, if we have ln, the inverse of natural log is e. So we're going to take e and raise both sides to that power. So e to the ln are inverse, they cancel. We have p equals e to the kt plus c. Now remember our power rule? If we have 7 to the 2 plus 3, that means it's 7 to the 5. 7 times 7 times 7 times 7 times 7. We have our 2 and we have our 3. This could also be written as 7 to the 2 times 7 to the 3. So let's use this property of exponents to rewrite this expression. So this is e to the kt times e to the c. Well, e to the c is just a constant in itself, so we can just call this a new c. So we're going to write p equals, and I'm going to put that constant in front, c e to the kt. This might be a formula that you're familiar with from Algebra 2 on compounding interest. So now we have solved it. We have a formula for p, and it didn't give us any information to find c or k, so it's just some general formula. And this formula is actually very important because it will simplify a lot of our work if we can go directly from a directly proportional relationship to this formula. Not every case will you be able to do that, but if you notice a directly proportional relationship with just one constant and one variable, using this formula will simplify your life. So let's try and do that. If dy dt equals negative 2y, and if y equals 1 when t equals 0, what is the value of t for which y equals a half? Well, I recognize that this is a proportional relationship. So I can skip a lot of the work of integrating by just recognizing I can use this formula. So here I will get y is my variable instead of p here, equals c e to the kt. Well, what's my k? Remember, this constant is our k. So we can rewrite this as y equals c e to the negative 2t. Now they give us some initial condition that we can use to find c. So if y is 1, we're going to put 1 equals c, that's what we're trying to find, e to the negative 2 times t is 0. Negative 2 times 0 is 0. E to the 0 power, or anything to the 0 power, is just 1. So we get 1 equals c times 1. So we just get c equals 1. So now we need to rewrite our equation. Y equals 1 e to the negative 2t. We don't really need to write this one here. Did we finish the question? No, we still need to answer it. What is the value of t for which y equals a half? So how do you think we will find that? Well, we're going to replace the y with 1/2 e to the negative 2t. And now we need to solve for t. Well, if we have e here, the inverse of e is a natural log. So if we take the natural log of both sides, these will cancel. So we get ln of 1/2 equals negative 2t. All that's left, get t by itself, divide negative 2. ln of 1/2 divide negative 2 is RT. Let's do another example. The weight of a population of mold is given by a differential function m, where m of t is measured in ounces and t is measured in days. The weight of the mold population increases with respect to t at a rate that is directly proportional to the weight. At time t equals 10 days, the weight of the mold is 100 ounces and is increasing at a rate of 2 grams per day. Write a differential equation that models this situation. Well, we need to write a differential equation. So we have d, and we're talking about m with respect to time, equals. It says it is directly proportional to the weight. The weight, we said, was m. So this will equal to some constant k, m. Now we need to find what this k is. So it gives us a little more information. At time t equals 10 days, the weight of the mold is 100 ounces and is increasing at a rate of 2 grams per day. So rate of 2 grams per day means dm dt equals 2 when t equals 10 and when m equals 100. So we can plug this in. dm dt is 2 equals k times m. Well, m is 100. Solve for k. So we divide by 100, divide by 100. We get 0.02 equals k. Now we can rewrite our differential equation using that value for k. dm dt equals 0.02 m. Let's try one more example. Bacteria in a certain culture increases at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, write a differential equation that models this situation. So the bacteria, I'm going to call that B, increases at a rate proportional. So dB dt equals some constant proportional to the number present. So that's B. So now we need to find this K value. Well, they tell us the bacteria doubles in 3 hours. Remember our formula that we wrote? P equals C e to the kt. This C represents an initial amount. So if the bacteria doubles in 3 hours, and if we started with C, this means 2C when t equals 3. So let's write that. 2C, 2 times the initial amount, equals C e to the k times 3. Well, now, if we have C on both sides, we can cancel them out, because if we divide C, we'll cancel on both sides. We get 2 equals e to the 3k. Well, now I only have one variable. I can solve for this k. To solve for this k, what do I need to do? I need to take the inverse of e, which is natural log. So I take the natural log of both sides. I get ln of 2 equals, natural log and e cancels, 3k. To solve for k, just divide 3. ln of 2 divide 3 equals k. Did I finish? No, I need to rewrite this differential equation. dB dt equals ln of 2 over 3 times b. That is our differential equation. So I hope you've learned a lot from these 5 examples of how to express relationships of differential equations if they're proportional or inversely proportional.